Okay, so I'll start now. So today we'll be learning about fluids. So first of all, in our introduction, solids, atoms are close together and can't move much, and the volume and shape are always the same, and it cannot be compressed. For liquids, the atoms are more free and are able to move past one another, and it takes the shape of the container it's in. So you can see that in this picture. The atoms are able to move easily, and depending on the shape of what the container it's in, it will be in that shape. And for gases, the atoms are far apart and there's no set volume or shape. Okay, so density is the mass in a volume. For example, as you can see in these pictures, these two objects are lighter, obviously, than this object. This object probably like metal or something, or iron. So depending on the masses, it'll either float or sink. So using this equation right here, this says P right here, but the density for density is actually rho, which is the Greek letter. So it looks like this, which is like a P, but not a P. And it equals the mass divided by the volume. So in the pictures above again, for this object, the metal is probably the mass is probably like more than these two. So let's say the mass is 20 kg. And again, the volume for each of these is the same. It's like the same water level. So the only thing changing in each of these things are the mass. So since this is 20 kg, it's probably gonna the volume probably be smaller than that, like 4, and it'll go down. And these objects will stay on afloat because the masses are probably smaller. And now we'll talk about pressure. So in pressure, in physics, pressure is the effect of a force acting upon a surface. Mathematically, it is a scalar quantity calculated as the force applied per unit area, where the force applied is always perpendicular to the surface. So if an object is underwater, let's say this is underwater, and there's an object here, the forces will be like this way and this way. And you can write pressure as force divided by the area. And the SI unit for pressure is pascals, which is equivalent to newtons over meters squared. And you can see for forces, the unit is newtons and area is meters squared. Okay, so you guys can do this example for pressure. Okay, so for this question, it says you're drinking a juice box. In the process, you suck all the juice and air out of the box. The top of the box is 7.5 centimeters by 5 centimeters, and the air pressure is 1.013 times 10 power 5 pascals. So it asks how much force is acting on the on top of the box. So it would look like that. And you would use the equation pressure is equal to force divided by area. So trying to find the force, it would be pressure times the area. And you know the pressure and you know the area. So the area would be 0.075 meters times 0.05 meters. And if you multiply that together, you would get 0.00375 meters squared. And you know the pressure is that. So if you multiply them together, you get 379.875 newtons for the force. You guys understand that question? Okay, so another thing about pressure is if you're running it is force divided by the area. The force is most likely to be the weight, and it'll be mg over a. And from our density equation, we know that it'd be mass divided by the volume, and the mass would be equal to the density times the volume. So you can also write pressure as rho times V times G divided by the area. And since this is a box, or like most things will be a box, it'll be V can be written as the area times the height. So you can cancel the area and it'll be this the density times G times the height. Okay. So this is the pressure if two force pressures are acting on a box. So you can see that in this picture, there's a pressure going downwards, or there's a force going downwards, and because pressure is equal to force over A, so this would be the force. And there's a force going up, and there's also the weight going down. So the total force would be the force going up minus the force going down minus mg is equal to 0. So you can write it as that. And you know that this is the density and this is the mass in terms of density and volume. So you could write it as this. The pressure of the second times the area is equal to the pressure of the first times area plus density times volume times g. So you know the volume is the area times the height, and then you can replace v for this equation and you get rho times g times area times height. And if you cancel out all the areas, then you get this equation right here. Okay, so if the object is close to the water, like over here, then instead of it being like this, then this pressure would actually be the atmospheric pressure, which is the pressure that is in the atmosphere or air. So it'd be like it would be written as this instead. So the equation could change based on where the setting is. So you can do this question now, and I'll give you a minute to do it. Okay, so I'll explain the question now. So, since you're already given the one of the pressures, it would just be, if we're trying to find the pressure of point A, for example, it would be the pressure of A is equal to P1 plus the density times G times H. So it would be written as 1.013 times 10 to the power 5 plus 1000 times 9.8 times 5.5. Also, this pressure right here, since it's closer to the surface, this is actually the atmospheric pressure. And I forgot to say before, but this is the value of the atmospheric pressure, 1.013 times 10 to the power 5 pascals. So after you solve that, you get 1.55 times 10 to the power 5 pascals. And since A and B are in like the same positions, the pressure would actually be the same for point A and B, because nothing is changing in both equations. So Pascal's principle is the change in pressure at any point in a confined fluid is transmitted everywhere throughout the fluid. This is useful in making hydraulic lift. And this is an example of a hydraulic lift. So you can see that there's a force going down this way, and this is the distance between them. And the area 1 is for this area. And this is the area of the second one. And there's a car on top of here. And there's a force going this way, because when you put a force through this, it goes like that. So you can write it as the equation F1 over the force of this one divided by the area of this is equal to the force of this one divided by the area of this. So, and if you do cross multiplication, you do this and that. You get the force of one times the area of the second is equal to the force of the second one times the area of the first. So that's basically saying that since this area is larger than the first area by a lot, it basically means that a really large force is the same as having a really small force. So a really large force on a small area is the same, is able to lift up this car. So this is a useful equation to know if you want to solve. Okay, so buoyancy is the measure of the upward force a fluid exerts on an object that is submerged. So, for example, if a box is underwater, then the buoyancy force is what keeps it afloat, because it's acting against the weight, which is mg, and it's the force. So that's what keeps it afloat. So for buoyancy, another example again, this is the box. So if there's two forces like that, then this would be the bottom force. This would be FB is equal to E times A. And this is the bottom pressure, since it's the pressure over here. And this is the one over here, which is B top times A. So the buoyant force would be the bottom times A minus the top times A. And you know you can write pressure as rho times G times H. So this is basically just the difference between the heights. So it would be a point is equal to times G times H bottom times the area minus the top times the area. So you can write everything on one side like this. So that's bottom minus the top. So this would just be the height, the change in height of the can, which is just the total height. And you know that the area times the height is just the volume, so it'd be rho times g times v. And rho times v is just m because the density equation. So it'd just be mg. So you get this equation. The buoyant force is equal to the weight done. So this equation, when stated in words, is Archimedes principle. And Archimedes principle is a statement that the buoyant force on an object is equal to the weight of the fluid displaced by the object. So now you can do this example for the buoyant force. Okay, so I'll explain the question now. So I wrote the equation here already. The buoyant force is equal to the weight. So a flat bottom barge loaded with coal has a mass of 3 times 10 power 5 kg. That's times. The barge is 20 meters long and 10 meters wide. It floats in fresh water. What is the depth of the barge below the waterline? So since you know that the buoyant force is equal to the weight, you can write buoyant force as W, the mass of the water, or the mass displaced by the water times the volume is equal to the mass of the barge times the volume of the barge. And you can write mass again as for density as rho times, oh sorry, this is not the volume, this is G. So it's rho times V times G, displaced by the water is equal to the mass of the barge times G. So you can cancel G out because it's just the gravitational acceleration constant. So, and you know, volume is equal to the area times the height. So you can write rho times A times H is equal to the mass of the barge. So you're trying to find the depth of the barge below the water line. So you're trying to find the height. So its height is equal to the mass divided by the density times the area. So the mass of a barge is 3 times 10 power 5. And the density of water is 1000. And the area is 20 times 10, which is 200 meters squared. So if you do that math, you get 1.5 meters. Okay. So now I'll talk about continuity. So in this diagram right here, um, there's the area right here, and this is the velocity is going through a mass going through here, and you can see this is the distance. I mean the length, and right here is the area of this part, and this is the distance, and this is the velocity. So you can see that when it's over here, it goes faster compared to when it's going here. So you can see this equation here, and you can see that since it's like the density is the same, which is probably going to be water, you can just cancel out the density in this part. So it's be the area of one times the velocity of one is equal to the area of the second one times the velocity of second. So it shows that this right here, this is a smaller area and this is a larger area. So that means that for these to be equal, this velocity will be a lot larger compared to the velocity of this one. So the amount of mass that flows through the cross-sectional area A1 is the same as the mass that flows through the cross-sectional area A2. So since it's the same mass, then the velocity for in this area would be higher than this one. So this is also a useful equation to know. Okay, so now I'll talk about Bernoulli's equation. So as you can see in here, this is the equation here. So these two are the pressures in these different spots. And this is basically like the work energy conservation, which is work is equal to the change in kinetic energy plus the change in potential energy. So it can be written as this. So this is the pressure of 1 point times the potential energy, which is the density times the gravitational acceleration times the height. And this is the kinetic, which is the density times the velocity squared. And it's the same on this side, except for different points. Okay, so you can try this question right here. Okay, so um, actually, I'll give you another. Yeah. Okay, so this is I have a question that needs Bernoulli's equation, so it would be P1 plus the potential plus 1/2 V1 square is equal to the second pressure plus so it says a nozzle is connected to a horizontal hose. The nozzle shoots out water moving at 25 meters per second. What is the gauge pressure of the water in the hose? And the diameter of the nozzle is much smaller than the inner diameter of the hose. So in this situation, since it's not the height's not changing, these two y's would be the same, so you can just cancel out those already, since it would be the same thing. And the pressure of the second part would be used to be the atmospheric pressure. So you can write it as P1 plus 1/2 rho V1 squared is equal to P2 or P atmosphere plus 1/2 rho V2 squared. So, and if you put the pressures on one side, it would be P1 minus P ATM is equal to 1/2 rho V2 squared minus 1/2 rho V1 squared. And I can write that as 1/2 rho times V2 squared minus V1 squared. And since you're trying to find the pressure, this pressure here, all we need to know is the velocity. So in the equation before, V1 times A2 is equal to V2 times A1. And for a nozzle or a hose, it would look like this. And the area of the circle in this situation would be pi r squared. So it would be, if you're just trying to, since you already know that V2 is 25 meters per second, trying to find V1, V1 would be equal to V A1 over A, oh, sorry, A1 over A2 times V2. And the areas would be the same, so we cancel it out. Or actually, it would not be the same. It would rely on the distance for the nozzle and the hose. So it would just be D2 over D1. So if this diameter is a lot, since you know that the diameter of the nozzle is much smaller than the inner one, then the diameter of the second one will be a lot larger, therefore making V1 a lot smaller than V2. So in the equation again, right here, if you bring it like this, then it would just be V2 squared, since if V1's extremely a lot smaller than V2, you can just neglect it and just say it's 1/2 rho times V2 squared. So now we know that, now that we know everything, we can write P is equal to 1/2 rho times V2 squared. And that is equal to 1/2 times 1000 times 25 squared. And then you get 3.1 times 10 to the 5 pascals. Okay, so now you guys can do problem 1. Okay, so for question 1, it says a fluid flows into a pipe with a diameter of 2 meters at a rate of 5 meters per second. If the other end of the pipe has a cross-sectional area of 0.5 meters squared, what is the speed of the fluid as it exits the pipe? So you would need to use the continuity equation. So it would be A1 times V1 is equal to A2 times V2. So it would be 0.5 times V2 for this side, and for this side be so it would be pi r squared, and since the diameter is 2 meters, the radius would be 1. It would be pi times 1 squared, which is just pi. So it would be pi times 5 meters per second. So V2 would just be equal to 5 pi divided by 0.5, which is just 10 pi, which is just 31.4 meters per second. And you guys understand this one? Okay, so here's the solution. All right, so I'll give you 2 minutes to do this one. Okay, so for this question, it says the reason why coconut floats in water is because, so if it's in water and there's a coconut right here, the only forces acting on it are the weight and the buoyant force. So the answers are the surface area of the coconut contacting the water is the same as the surface area of the water contacting the coconut. So that is not correct. The gravitational force acting on the coconut is less than the buoyant force. That is correct. So if the gravitational force, which is this, is less, then that means the buoyant force is larger, which is keeping the coconut on top. And these other two are wrong. Okay, this is the solution. Okay, so this is a question for you. Okay, so for this question, a baseball has a mass of 500 grams, but it weighs 4.7 newtons when completely submerged in water. What is its volume, assuming that the density of the water is 1000 kg of m cubed? So the buoyant force would be equal to the density times the volume times g. So, and you also know that the buoyant force is equal to the weight, except the weight in this question is changing. So it would be 2 minus weight 1. And you know weight 1 is 4.7 newtons. And to find weight 2, it would just be mg, which is 500 grams times 9.8, which is 5 kgs. I'm sorry, 0.5 kgs times 9.8, and that's equal to 4.095 newtons. And if you subtract them, it would be 0.205 newtons. So the density, so you know the force is 0.205 newtons. You know the density is 1000 kg per meter square, meter cubed, times 9.8 is equal to times v. So v would just be equal to 0.205 divided by 980. And that's equal to about 20.9. Oh, sorry. Yeah, so it's like 22.09 times 10 power negative 5 meters cubed, or 20.9 centimeters cubed. So this is the solution. Okay, so this is question 4. Okay, so the question looks difficult, but it says the tubing in the container on the left where there's a gas at an unknown pressure. The tubing connected to the container is open to the atmosphere, which has a pressure of 760 atm. So like this area around. If the liquid contained within the tube shows a pressure difference of 77 atm, as in the above image, what is the pressure of the gas container? So since the water, if you put a force down, the water would go in there. So there's a pressure that's acting on the water, stopping it. And since you know the open to atmosphere pressure is 760 atm and the difference over here is 77 atm, you just add them together. It would be 837 atm. So it would just be this. Okay, so you guys can do this question. Okay, so in this question right here, a submarine cruises at a depth of 300 meters. What is the pressure at this depth? So you use equation P1 is P ETM plus rho times G times H. So you know PDM is right here, 101.3 kPa, which is 1.013 times 10 power 5. And then plus rho, which is 1000, which is the density of water, times G, which is 9.8, and times the height, which is 300 meters. So you can just solve that to get the density, the pressure. So this is the, I didn't write a solution for that one. So this is question 6. Okay, so for this question, a liquid flows through a pipe with a diameter of 10 centimeters at a velocity of 9 centimeters per second. If the diameter of the pipe then decreases to 6 centimeters, what is the new velocity of the liquid? So we'll see the continuity equation, which is A1 times V1, A2 times V2. So the diameter of the first part is 10 centimeters, so the radius is 5. So the area would be pi r square, which is just 25 pi centimeters squared, and the velocity is 9 centimeters per second, and decrease to 6 centimeters. So the radius is 3, so it would be 9 pi, and then times v2. So the new velocity would be 25 pi times 9 divided by 9 pi. So cancel this part out, and you just get 25 centimeters per second. All right, so this is the solution. And you can do question 7. Okay, so if a pipe with flowing water has a cross-sectional area of 9 times greater at point 2 than at point 1, what would be the relation of flow speed at 2 points? So again, you would use A1 times V1 is equal to A2 times V2. So if the cross-sectional area is 9 times greater at point 2, then it would be 1 to 9. So it'd be V1 is equal to 9 V2. So it would say that the velocity of at this point, at point 1 is 9 times greater than at point 2. And this is the solution. Okay, so this is the final question. Okay, so I'll explain this really quick. So you would again use the equation A1 times V1 is equal to A2 times V2. And to find the area would be pi r squared. So um the first of all, it would just be the diameter, so it'd be the pi times d over 2 squared, which is pi d squared over 4. And then it can fix to half. For this be A1, and for A2, it would go to half, so it'd be pi times d over 2 squared divided by 4. Is pi times d squared over 4 divided by 4, which is just pi 1/4, 1/16 pi d squared. Which is just 1/4 of A1. So it would be A1 times V1 is equal to 1/4 A1 times V2. So cancel out the A1s and get V2 is equal to 4 V1. So the new velocity is 4 times the original velocity. Okay, so that's gonna be it for this week. I hope you guys have a great weekend.